So it's my pleasure to introduce Yasaman. So we've kind of worked together on this physicsy perspective on deep learning for quite a while now. And she has been very good working on a lot of, very productive, working on a lot of different projects. And today she's going to tell us about this large learning rate phase of deep learning, where I think the background here is that a year, 2 years ago, there was like this big breakthrough in understanding of deep neural networks in terms of this thing called neural tangent kernel, which roughly says that when the learning rate is very small, the neural network evolves like a linear model. And Yasaman has done very good work on this. But now she's going to tell us what's going beyond this kernel phase. And so take it away, Yasaman.
Thank you, Greg, for the introduction and also for the invitation to give this talk here. So the work that I'm mostly going to be talking about today is joint with Aitor, a lot of former physicists, so Aitor Lukowitz, Ethan Dyer, Joshua Zoll-Dickstein, and Guy Garari, whom many of you may know. Actually, I was going to start with a couple slides of just background context, which will cover a little bit of the how we got to this project, like the history of our work before this, also related to the neural tangent kernel. So I'll start pretty broad, do a couple slides of intro, and then actually get into this particular topic. Maybe like before I do that, I want to have one like philosophical slide about how I pick problems in this area, because I like to work more on kind of empirical and theoretical foundations of deep learning, trying to understand what's going on, but working closely like with the computer science community, where they're very they're interested in impact and you know, large-scale systems and questions that are very relevant to the real world. So, you know, in this space of like understanding how deep neural networks learn, there are many open questions related to how the algorithm and the architecture and the hyperparameters and the choice of the task that you're training on play a role in the final result. I think so. There are a lot of unknowns, and so how do you pick a problem kind of in this space, since it is, after all, like an artificial system? We've designed it completely and we're in control of that, as opposed to, say, systems we're used to in physics. And this is a problem that I think about a lot, because I'm not sure what to do in an artificial science as opposed to nature. But one thing that I tried to think about when picking problems is usually computer scientists have something in mind, some target of interest, because at the end of the day, these are models that are kind of deployed in the real world. We use them for specific tasks. So performance or generalization is, of course, one of the biggest ones. It's you know, the benchmark thing that everybody thinks about. But in other contexts, people kind of demand other things of their models. They want their models to be confident, robust to certain kind of shifts in the data distribution. Maybe they want some guarantees on privacy, so that you know, when you do inference on a model, you're not actually leaking information from the training set, and fairness and all sorts of things. So that's just to kind of say that in this broader space of just understanding deep learning, we're kind of, at the end of the day, trying to relate to something that is deployed in the real world, and the constraints that we're putting on the problem are pretty artificial. They're our own kind of human constraints that we want out of the model. So with that said, this talk is kind of in some ways motivated by thinking a bit about generalization, like where do the best performing networks tend to lie? Although that question is pretty hard to answer, of course, because it's very task dependent. And so you know, the context in which I'll be talking about it really is just a few image classification benchmarks. It would be nice if we could kind of have, if there were some more general understanding of where do the best, you know, performing networks tend to lie in general. So generalization of performance was one kind of reason we went down kind of thinking about this particular problem. Another is trying to kind of partition the space of this large space, design space that you have of models and algorithms and hyperparameters in there, however you want to divvy that up, into distinct classes. And basically, with this talk, one of the goals will be to kind of walk away with an understanding of there being maybe two broad classes that kind of connect to, one of which connects to existing theory and one of which we don't know yet fully how to describe. And then it's also connected to our previous work, which is kind of motivated with similar things in mind. So here I want to maybe go through a couple background slides on what's known currently, or high-level summary of some of the work on infinitely wide models. So the one motivation for this was sort of an overarching trend in deep learning, which has been towards overparameterization, whether that overparameterization comes from width or depth. Now, I think those two should be distinguished, and I've seen maybe there are questions. Thinking about the case of depth is maybe tricky in some ways. So width is the one that I'm actually gonna focus on for this talk, where we're thinking of networks that have a fixed depth, but we continue to make them wider and wider, and we're interested in how to describe their dynamics under gradient descent. These plots on the right are now very old plots. They're some of the earliest plots I remember seeing when I kind of thought about working on this topic, which kind of show the test error as a function of both number of parameters in this case, but also number of hidden units, so the width of a layer, as you make, how the test error continues to improve as you make networks wider and wider. And so, work such as the one that I'm showing here and many other empirical work, which I'm not showing, kind of suggested or pointed to the idea that neural networks in the infinite width limit might be an interesting thing to study. So that kind of led us down a route where we thought about how to describe networks in the infinite width limit, and particularly to do it in function space rather than parameter space. So, the first line is kind of just describing the iterative computation that a feed-forward neural network does. So you take the inputs at layer L-1, pass it through a nonlinearity phi, multiply by an affine transformation, get the output for the next layer, f to the L, where the subscript indices here index the hidden nodes, and you have n hidden units. If you kind of think about what happens to how to describe a network at initialization, you start out with usually some prior distribution over your parameters. Oftentimes, they express how much knowledge you kind of have about the problem you want to solve at the beginning. Oftentimes, we start with priors over parameters that are distributed IID. And so that, coupled with this n going to infinity limit, kind of allows you to apply a central limit theorem in this limit to get that the distribution over the kind of computation done at every hidden node. So I'm going to call these f sub i's pre-activation values for hidden node I. That you're going to get that it's distributed as a Gaussian process, or the finite version of it is a multivariate normal distribution, or if you like, a Gaussian field theory. And this is kind of coming from the central limit theorem that you're summing over, if you like, I hope everyone can see my cursor, over infinitely many random variables. And one of the things you get out of that is also, so you get kind of a recursive or iterative computation you do in the space of kernels. So to describe this Gaussian process, you need a mean and covariance function. And this covariance function is the recursion relationship for it, kind of in one setting for a feed-forward network, is in this boxed equation. So it tells you how, if you have the covariance function for layer L-1, how to kind of propagate it forward to get the covariance function or the two-point function for that distribution for the next layer. And then there are other things that happen here. So once you have this mapping, you can do exact Bayesian inference. So there's work from the 90s, really, and that was what inspired us to go this route, which had done this for a single hidden layer network. Nice work by Radford Neal. Since we worked on it, many others, it has been extended to other architectures. Notably, Greg actually has some really nice, quite technically, tour de force work on extending this to treating the case of general architectures and proving the GP correspondence. So I encourage you to check that out. And also work by Sho Yeda, kind of backing that I'm aware of, where he's backed off kind of the infinite width limit and computed corrections to the GP prior and Bayesian inference. And most recently on Twitter, I saw kind of work by Jim also in this direction. So a lot of nice work kind of coming out of this and continuing in this direction. But this is not the main focus of the talk. Really, this was kind of the evolution of the story. We thought about functions. Now we'd like to ask about how do such networks in the infinite width limit behave under gradient descent? And I kind of just want to flash these equations to show, just what happens from a simple change of variables. So all I'm doing here is kind of taking the evolution equation or gradient flow equation that you have. So theta dot is equal to minus eta times the gradient of the loss with respect to theta, and rewriting that in function space. Just with chain rule. So here, the intermediate variables are kind of the values of the function at the training data points, which are denoted by x sub alpha. And if you do this change of variables, what you'll find is that the evolution of the function in time is given by this equation, which kind of has a term that kind of controls the error. It's the derivative of the loss with respect to the function times this other thing. And this other thing is what I've put in parentheses here. It's this dynamical variable, which comes from taking the gradient of the neural network output with respect to the parameters, contracting it over all the parameters, and you get this this thing that is it's a kernel. Now, in general, this box equation may not be very useful to you because I didn't tell you how this new variable theta sub t evolves in time also. And in general, what would happen is if you tried to write an evolution equation for theta sub t, you would get kind of new contractions of gradients, including higher order gradients, which would be new objects for which you would also need to write down kind of their evolution equations and so on. I'll kind of come back to this towards the end of the talk. But what that means is kind of doing this naively, just changing variables to function space is maybe not super helpful unless you make some further approximations. So i.e. this equation is not closed in general. I need to write down kind of a hierarchy of further variables to evolution equations for further variables in order to actually solve this. But what turns out to be miraculously true, and this is what Greg referred to at in the introduction, is that this dynamical variable is actually frozen at its initial value in the infinite width limit under certain conditions. And so this result was published kind of in NeurIPS 2018 and many others kind of concurrent works that looked at this problem kind of through a similar lens with similar results, which I'm not listing here. So this is definitely not kind of a thorough citation list. But this dynamical variable is frozen at its initial value. I'll refer to, I'll use the term neural tangent kernel to just refer to the dynamical variable and not just the quantity at initialization, even though kind of the way that it was originally, how it was originally used was to refer to the thing at initialization. So we want to kind of think about this as a dynamical quantity, and it'll play a central role in the rest of this talk. One of the outcomes of this, as I kind of alluded to as well, if this thing is just constant in time, and let's say you have mean squared error loss, so this thing is just linear in f, then you can solve this equation exactly and get the exact solution to dynamics. And it also builds a correspondence between gradient descent in these infinitely wide networks and regression with a fixed kernel, which is also kind of a class of very popular machine learning methods. But the kernel here is sort of new. It has a different structure than kernels that have been studied before. And this asterisk about under certain conditions is kind of the heart of this talk. So I think it was maybe not as appreciated in some of the earlier papers that, well, what are exactly the conditions under which this holds, and particularly it holds up to some maximum learning rate. And I'll come back to this later, but basically if your learning rate is small enough, this result will hold and not if it's too large. And then there's some kind of other connections between kind of the kernel viewpoint and how the model would behave effectively in parameter space. So it turns out that if you know, that dynamics I just described is equivalent to training a first order Taylor expansion, which I'll refer to as a linearization of the model about its initial parameters. So if you just take this model, you know, Taylor expand it, drop the t variable, but like just define a model like this, and then train that. You will find that in the infinite width limit, they should agree. And in general, there kind of is a correspondence or back and forth. It's in machine learning called the kernel trick between kernels and linear models that are constructed from their features. And here are some empirics that show that, at least in certain regimes, the nonlinear models can be described by their linearization. So this is like one block of a wide ResNet model trained with SGD. It's pretty wide. So in this convolutional setting, the width refers to the number of filters in a convolutional layer, and this is width 1,000. And the agreement between the solid and dashed lines is pretty good until up to some late times. Here in the plot on the right, you already start to see some of the discrepancies, and this discrepancy would set in earlier if the network were narrower. So kind of for a lot of the models that you would just sample randomly in practice, let's say from your from models you have saved in your library already, they're probably not described by their linearization out until late times in training. Okay, are there any questions about this background? If not, I will kind of now actually focus on what this talk is really about. For the rest of the talk, everything I'll describe is very specific to mean squared error loss. Different loss functions would exhibit different phenomenology. So how we got started on this was kind of from a bunch of different collected observations. One was that nonlinear models tend to perform better than their linearized counterparts. So there's some part of this like performance kind of question that we weren't capturing maybe if we were studying linearized models. I will distinguish that from studying infinitely wide kernel methods, because a linearized model here refers to the thing you get when you Taylor expand the finite width model, which does perform differently than an infinite width model. So those two are kind of are somewhat different, and maybe good to keep in mind. Not, you know, the general observation tends to be that the best performing models tend to be very nonlinear if you're thinking about a comparison between models of the same size. Another observation was this one that kind of, I think, maybe people knew but wasn't appreciated as much, which is that nonlinear models are also trainable up to larger learning rates than are accessible for the linearized model. And in many practical settings, we tend to use large learning rates. Now, whether those large learning rates actually fall into this very nonlinear regime or they fall closer, within this bound that I described, I think is unclear to me. But there is a regime kind of larger learning rates which the linearized model simply can't access, and we do train sometimes in that regime when we choose hyperparameters. If you think about the linearized problem with MSE loss, it's a convex optimization problem, so it has a maximum learning rate, which you can just get from a textbook. But can we say more about, say, when the nonlinear problem breaks down, and also how to describe it in this other learning rate regime? I'm not actually going to be able to answer that last bullet point in full. I think it's one of the, it's an open question in, I think in deep learning theory, how much you would actually be able to say about the evolution of models in this large learning rate regime. But this is maybe kind of a first step at least highlighting, characterizing kind of some of the boundaries of that regime and also some kind of general phenomenology that goes along with it. So here's another way I want to kind of motivate this, which is we're trying to kind of break up this space of hyperparameter. We have a single hyperparameter, which is the learning rate. And we're trying to partition kind of the space of this hyperparameter, and ideally in a more general program, like even more hyperparameters, into meaningful classes. Meaning, if two models are in the same class with the same choice of hyperparameters, maybe they behave roughly the same way. They exhibit kind of similar dynamics. And you get a similarly trained end model. What I want to suggest is that we're going to like break up this axis into a small and a large learning rate regime. There's of course also this divergent regime, which everybody knows. If you pick a learning rate that's too large for the problem at all, it will just diverge. But we're going to use this quantity lambda naught to kind of demarcate these boundaries. And this lambda naught comes from the top eigenvalue of the neural tangent kernel, which was this kernel function that I mentioned a couple slides ago. Comes from the top eigenvalue of this neural tangent kernel at initialization. And if you want a comparison to the Hessian, it's roughly the top eigenvalue of the Hessian. And it's exactly the top eigenvalue of the Hessian in the limit of infinite width when you're thinking about initialization. And this is because the Hessian, for the case of squared loss, has these two terms, one which comes from kind of the second derivative of the loss, one which comes from the first derivative of the loss with respect to the function. And this first term kind of, again, looks kind of like the NTK formula that I wrote down, except that the contraction is over the data indices rather than the parameter indices. But these two are kind of share the same, these two matrices with the NTK would share the same non-zero eigenvalues. And that's why their top eigenvalues are the same. And then there's the second term. The second term kind of dies out as you make the networks wider and wider, so that it effectively just collapses to this first term. So there's a quantity lambda naught that we're going to use to kind of demarcate these different things in this following way. So there's a first boundary, which is 2 over lambda naught, which I'll refer to as eta critical. This is the thing that kind of was shown in previous work, also our paper, other papers as well. That tells us when kind of the NTK validity breaks down. So for learning rates kind of to the left of eta critical, as you make networks wider and wider, you would expect your dynamics to come in closer agreement with the NTK theory. I referred to this, or we referred to this phase as the lazy phase, kind of in connection with another paper that also called a paper by Chazot and collaborators that also use that terminology. We use it kind of in the context with the idea that it refers to the first order Taylor expansion of the network, or the dynamics being governed by the first order Taylor expansion of the network as you make networks wider and wider. But that's slightly different than what was considered in the Chazot paper. So that's maybe just a minor point, but we're using the same terminology. So this is a regime which kind of at finite width, it's just a regime, and I'm going to try to argue that it's actually like a phase in the sense of it being separated from the catapult by an actual phase transition in the infinite width limit. 2 over lambda naught is what you would get if you kind of looked up the convergence of gradient descent in a textbook. But what's new here is that before you actually diverge, you get this other regime, which exhibits very different phenomenology. Sorry, a pop-up just came up. Exhibits very different phenomenology, which I'll go through in a moment. We don't think it connects to any existing infinite width theory. And then this other kind of transition before the divergent phase, as we find empirically, tends to happen at a maximum learning rate, which has the form C over lambda naught, where C tends to be kind of a simple number, sometimes close to 4 for a lot of architectures, except for ReLU networks, which are closer to 12. And this is not exactly true, it's kind of approximately true. The experiments I'm going to show you are not like precision tests of this sort of thing, but they are like robust. They're kind of more tests of the robustness of these 2 phases to the setting of other hyperparameters. So that is to say, and I should have probably mentioned this earlier, for instance, right now I'm thinking about just constant learning rate SGD, or constant learning rate kind of full batch GD. But a lot of our experiments are really just SGD and not full batch. So the effect I'm describing is not coming from stochasticity. It's kind of just resilient for the most part to the effect of stochasticity. Another point I want to make is that although I'm talking about constant learning rate SGD, we are thinking of this mostly, we think the important effect is really the choice of learning rate early in training. So you could have learning rate decay. In many of our experiments, we do have learning rate decay, but it's really the choice of the initial learning rate. If you use it for a sufficiently long period of time, that kind of determines whether you're more lazy or in the catapult regime. So those are just kind of side points. The theory is in this very kind of controlled setting of full batch, even full batch and constant learning rate gradient descent, but the experiments are kind of robust to this sort of these choices. So eta max, as we find empirically, kind of has this form where this C is an architecture dependent constant, as I mentioned, which most strongly seems to depend on the nonlinearity. And then I'll show a simple model where this constant is exactly 4. And so kind of we thought it was interesting that that came up both in the theoretical model and holds pretty well for a certain class of networks kind of in practice also. And this new regime, I guess the biggest takeaway from the slide is that this new regime, which we term the catapult phase because of kind of qualitatively what we imagine happening is that it's there's an initial basin in the optimization landscape that you initialize in, and would be related to what you would explore if you linearize the model and train that. And with the catapult, what you do is kind of leave that basin very quickly because your learning rate is too large for the local curvature of that basin. And so you kind of very quickly early in training move to some other basin and then evolve there. But that's just rough terminology for kind of the qualitative picture. We're going to make some things more concrete in an actual model. Any questions so far?
Yeah, I have a question.
Yeah.
So the breakdown of the linearized model, you should be able to give the functional dependence of the of the next leading term in the Taylor expansion as a function of the learning rate and the width of the network. Do you know the functional dependence of the next order correction?
That's a good question. We have not done that sort of analysis in detail.
I mean, can you go back to slides maybe?
Yeah. Earlier?
No, this one was good. For example, here you said that the second derivative or the second term dies out in the infinite width limit. In
Yeah.
h mu at the bottom. So how does it die out? Is this?
So that would be if you kind of evaluated kind of expectation values of that quantity or moments of that quantity at initialization as a function of width. For the thing I think you're describing, I think you could do it if you kind of, yeah, you could, what ends up happening is that, so we kind of have a function space picture for what happens here and not so much a weight space picture. But what happens is that the function starts to grow quite rapidly for this case of MSE loss in the catapult phase. And that also leads to a large growth kind of in the weights. So in the Taylor expansion, when you have kind of these higher order terms that determine the change in weights, you could kind of, if you kind of plugged back in there, I think you would find that a lot of them, maybe you would find kind of the condition, another condition that should be equivalent to this for when that would start to diverge. But what we try to argue in this paper, although we don't flesh out the argument, we didn't fully write up the argument, but believe it's true, is that all the terms kind of become of the same order as you go kind of, so all of the terms kind of in the Taylor expansion would start to have kind of the same order. Is that a helpful answer?
Yeah, just to make sure I understand, the second term is not zero term by term, but the entire sum cancels against many terms of the same order?
No, so are you thinking about why this thing is vanishing in the infinite width limit?
Yeah, and how it's vanishing. So okay. Parametric dependence of how it goes to zero.
So I think there are maybe two different, maybe this will become clear later, but when I was saying this vanishes, that was kind of evaluating at initialization. If you evaluate things at initialization and then ask about, if you like take the infinite width limit and then ask about time evolution, those two limits, we think they don't really commute. So you would have to kind of work to you would have to work at finite width. You would kind of evaluate this term. It would be small. It would, I don't remember, but it would, let's say it has like kind of, it's of the order like 1/n or something. But what you would find is that it's going to multiply a term like kind of weights squared. And the weights are going to grow by some factor that will also be n dependent. And so that second order term kind of, when you contract it with the change in the parameters, which comes from actually the dynamics, will cause the effect of that term to grow. And I think similarly for the next order term, in norm, it will also grow. So each one of those kind of will start to grow and have similar orders. Does that help?
Thank you, yes.
So it's not just, this is like, there's this tensor, but it's contracted with, in the Taylor expansion, it's contracted with the change in the weights. And the change in the weights and the change in the function is something that's going to grow with in this catapult phase, which is going to cause, so if this term was suppressed originally by like 1/n because it was contracted with a small change in the weights. So like here the change in the weights is going to be, the second term is going to drop out. The second order term drops out because also like the change in the weights, if you solved, say, this problem, would mean that the fully contracted kind of second order term where you contract the second derivative with the weights would be suppressed compared to this one. But in the dynamics that happens here, it's pretty non-perturbative. So the change in the weights will start to be kind of unbounded or grow with n, which will make all of these terms kind of order 1 and or growing rather than suppressed. So I think that's all to say just that I think that one would also want to account for the change in the weights or the change in the function, something that comes from the dynamics.
Thank you.
But I'm happy to talk about it more after the talk.
Yeah, thank you.
So let me check time. Okay, so I think I'm actually short on time. Before I talk about the simple model, which we have to kind of understand this, I want to talk about some empirical phenomenology. So signatures of the catapult phase that really distinguish it from the lazy phase. So one signature is that the loss in the catapult phase grows pretty rapidly early in training. And you can see that here, the like red and green curves in both of these plots are learning rate values that put you in the catapult phase, and the orange and blue values are put you in the lazy phase. And you see that the loss kind of goes up as if it's about to diverge, but then something kind of reels it back in and lowers it. And you see this for two different models. Like the one on the left is kind of a simple setting of ReLU fully connected networks on MNIST. But you see that kind of the same thing holds up on the right, even with wide ResNet. And this is a network with like batch norm, conv layers, skip connections, etc. Similar phenomenology holds. Another signature is kind of how the curvature evolves in these two phases. So here I'm just going to look at a single scalar, which is this top eigenvalue of the NTK, and look at its evolution with time. That's kind of, I'm using the word curvature here to really refer to lambda sub t, but roughly because of this kind of relationship between the Hessian and the NTK, you could kind of think of it roughly as the curvature that would come from the Hessian also, or analogously, if you like, rather than track a single eigenvalue of the NTK, if you track the full spectrum or tracked kind of the Frobenius norm of the kernel, I think you would see kind of a similar results distinguishing the lazy and catapult phases. And the distinction is that, of course, in the lazy phase, I told you that as you make networks wider, you get to the NTK solution where the curvature doesn't evolve at all. So theta is fixed, theta, the matrix or the kernel function is fixed, its eigenvalues are fixed, and you see that in these blue and orange lines. So these have some evolution, which is small here because it's a finite width, but that would vanish as you make the networks wider. Whereas these green and red lines are in the lazy phase, and you see that there's kind of a large, and in the theory, like an order 1 change in lambda early on in training, which causes lambda to decrease. And so it has some lower value. Basically, the scale of the NTK kernel, of the entire kernel, drops in the catapult phase early in training. And again, you see that here in the plot on the right also. And then another signature is if you looked at kind of the fact that this even for a finite width network, persists out to late time. So it's reflected in the value of the final curvature. So if you plot the final curvature against the initial learning rate, you see here that in this regime between the gray and the black lines, which is the catapult phase, the final curvature is much lower in general than it is to the left of the gray line, where it kind of stays at its constant, kind of close to its initial value. You also see that in general, we tend to find that the final curvature is less than 2 over eta, which is kind of what it would need to satisfy in order to kind of be consistent with being a linearized model towards the end of training. And so in general, we think that that's kind of like a bound for the final curvature. And we've tested that to some extent empirically. And these networks, because they're ReLU networks, their transition is closer to 12 over lambda naught rather than this 4 over lambda naught that I mentioned. And so that's why you see that the black vertical lines extend out that far, and the pink region is kind of the divergent phase. So that's to say that kind of the models evolve towards flatter regions as measured by this particular scalar, or as measured by the NTK. They move to flatter regions of the optimization landscape when they're kind of evolved in the catapult phase. So this is kind of the high level, again, summary of these 3 different regimes. In the lazy phase, roughly the model kind of behaves like its linearization. In the catapult phase, it very quickly breaks away from that. And C equals 4 is going to come out of our simple model in just a moment. This is a small aside kind of on 2 different ways to parameterize your neural network, because the model that I'm going to show is going to be parameterized in what we've been calling NTK parameterization. And in practice, what you're used to is standard parameterization. It's slightly different, and our experiments, many of them are done in standard parameterization, so we believe that the same phenomenon kind of holds there as well. So NTK parameterization, first place that I saw it was actually in the NTK paper. What it does is, rather than kind of initialize, maybe let me first describe standard. What you usually do when you initialize neural networks is you'll multiply by the weights, kind of like this, without any factors out in front, and then you'll kind of adjust the variance of the weights appropriately, so that the variance of the output for a single hidden node is of order 1. So kind of if the variance here per weight initialized IID is 1 over n, then summing over all of these, it would give something order 1. And so that's been absorbed into the actual parameters. Whereas what you could have done is kind of factored out that that dependence explicitly at initialization. So put a 1 over root n out here, but then initialize each weight to be to kind of have variance that's order 1. So sigma squared w here is just a constant, and this kind of, both of them give you order 1 invariance outputs per hidden node, but they give rise to different gradient descent dynamics if you're kind of limiting the other hyperparameters you have in the problem. Like if you have just a single learning rate for the entire model, then these 2 lead to slightly different gradient descent dynamics. So they're not exactly kind of the same, but to the extent that we've tested this, we kind of see the same behavior in both of these settings. The first one is particularly nice because it just gives to nice limiting behavior as you make networks wider. So if you're kind of in this parameterization, what would end up happening is your kind of kernel function, as you made it wider and wider, would stabilize to some kind of, fixed value, and the top eigenvalue or that is to say, the learning rates which you would need to use, the maximum learning rates which you would need to use if you were training in NTK parameterization would remain kind of order 1 quantities as you make the networks wider. Whereas in standard parameterization, the maximum learning rate gets smaller with width as you make networks wider. And so just to take the kind of have some things stay finite in the infinite width limit, it's easier to use this top parameterization. So that's just a side remark. And that's what we kind of do in the theory, but in experiments, we test in standard. So let me go through kind of the highlights of the simple model, which recovers the catapult phase. So the setting is most general setting, which I'll have like one slide about, is the following. We have our model maps from R to the D to a scalar R. We have parameters which are in R to the P, and we have a full training data set. We're using MSE loss, and this was the definition of the NTK kind of now here with the 1/m out in front that I mentioned earlier. And the model we're going to use is just a single hidden layer network of width n with these two kind of weight matrices or vectors. U is the first layer weight matrix, V is the final output vector. I'm working in NTK parameterization, so again there's this 1/√n out in front. And so this is just single hidden layer identity nonlinearity. I'll come back to this full model with like multi-dimensional input and real data any data in a moment. I'll first walk through like the simplest version, which is where we kind of drop really the dependence on the data. We have just one-dimensional data. We have one training example, and we can, it doesn't really matter, but we can set the label to be 0. So in this very special case, our loss is just f squared. F is the dot product, inner product between V and U. And theta, which was originally a matrix that you would have to evaluate on kind of the full data set, here is just scalar because there's one data point. That scalar is lambda, and it's related to U and V through the norms of U and V. And so now in this very simple setting, we're going to do the same thing I alluded to at the very beginning, which is rather than think about gradient descent on the space of parameters, we're going to do gradient descent in the space of functions, or in the function space. So we have these two kind of evolution equations for U and V for gradient descent. And if you write down the evolution equation, the updates for F and for lambda, you would find the following equations. And what's really nice here is the fact that these equations are closed. So I mentioned in the beginning that if you kind of, in the most general setting, when you had this evolution equation for the equation for df dt in the gradient flow setting, or even if you did gradient descent, it depended on these other variables. It depended on the NTK, and the NTK depends on other things. And so you would have to say something about that kind of coupled system of differential equations. Or update equations. Here we just have to deal with two, which is really nice. Two scalar update equations. And also at initialization, the initial value of f naught and lambda naught are order 1 quantities. They're not width dependent. That's kind of how we usually initialize things, and kind of key to a lot of this. So let's try to recover kind of the phases very roughly. I'll just kind of sketch the argument for how to see it. We kind of want to solve these dynamical equations as a function of eta in the large width limit. We're not going to solve them exactly. We're just going to talk about really like their fixed points and their rough behavior. So let's recover the lazy phase. If you take the infinite width limit, you see that the second term here drops out and this term drops out. And so, the curvature is just constant. That's a sanity check that we recover the right result. And kind of the function f decreases by the same multiplicative amount every, or by the same multiplicative amount at each time step. And, you know, as long as this in magnitude is smaller than 1, which is this setting, which is this condition eta less than 2 over lambda naught, then this will converge. And it'll converge in a time that's not width dependent. It's kind of order one steps. And if you back off of the infinite width limit, you'll see that kind of here, lambda will get some order 1 over n corrections to it. But as long as kind of this thing is still smaller than 1 in magnitude, it'll make sure that f is shrinking and therefore the loss is shrinking, and lambda won't change much. And again, the same thing is true. You'll get convergence in a time that is, you know, to leading order is independent of width. And then there are some small like finite width corrections here that I've dropped that you could also account for. So that's recovery of the lazy phase. When eta is less than 2 over lambda naught, we kind of get essentially that lambda is constant or gets corrected kind of in a power series in 1 over n. Now for the catapult phase, so why is this setting different? What's different here is how this first term kind of behaves. So now this term is in magnitude, it's larger than 1. So what will start to happen is, you know, at initialization, imagine this term is of order 1 over n. It's small because f0, I said, was of order 1. This multiplicative term in magnitude is larger than 1. So f starts to get multiplied in by these factors that are larger than 1, and it starts to grow. Now on the other side here, lambda originally starts to receive small corrections because this is order 1 over n. This term, because eta is less than 4 over lambda naught, is also negative. And so the curvature will start to decrease, but it'll decrease by a small amount. This is the 1 over n correction, until you know, f is of an order that's large enough to break that condition. So you see that if f were to scale with n, then these corrections would start to be of order 1, and you would get large changes in the curvature. And so that's basically what happens here. F starts to grow due to this term, and it's allowed to grow kind of in an unbounded way. There's nothing to kind of reel it back in, really. Let me come back to what this second term does here. But f starts to grow, and when f has grown to be of order root n, then this term is order 1, and it allows for a large change in the curvature. The curvature will drop by some amount, and it'll drop by the amount that's needed to kind of make this term kind of less than 1 in magnitude again, because that's the thing that really allows this to converge. If it turns out that this thing in magnitude is not less than 1, f will not start to, f will never like shrink asymptotically. So so that's kind of what you start to see here. And the other thing I forgot to mention is that this growth in f kind of happens in a number of steps that's logarithmic in n. So for f to grow to be of root n, of order root n, you need a time that's goes as log of n. And that's maybe one of the key things that I want to emphasize, which is that there's a time scale here that, at least in the simple model, seems to diverge with width. If with respect to the second term, this other term that I dropped, what happens is, you know, this term can help you. So like 1 minus eta lambda tends to be, you know, negative, and it tends to be, you're worried about it being larger in magnitude than 1. And this can help you because it makes it a little bit more positive and shrinks it in magnitude. Even when f is, you know, at some point f becomes of order root n, and this term becomes of order 1, and it helps you by quite a lot. But even if that kind of starts to shrink f, at some point, F will also, once F starts to shrink, again, the effect of this term is quite small. And so you're going to be kind of governed by this 1 minus eta lambda term. And so that's why you kind of need the curvature to drop enough so that it kind of satisfies this lambda is less than 2 over eta bound, which comes from needing, F to converge because of this original multiplicative factor. So that was maybe a lot of words. Are there any questions about that? Kind of the interplay between those two things? So it's kind of, the point of these equations is that it's highlighting kind of a mechanism which is purely closed in this system for how F can grow, but lambda can bring it back in. And we get explicitly out of this model on what time scale that happens, how the function and therefore the loss should grow with width, and also like a concrete value for what eta max would be in this particular model. Any questions about that? So if not, kind of that's how you see the catapult phase happening. This is what explains the growth and the loss. And finally, for the divergent phase, if eta is larger than 4 over lambda naught, then this thing is positive. And because we have an F squared out here also, lambda will just start to grow in magnitude. Will just start to grow, and there's nothing that will bring it back in. And you need lambda to be small to have this term be small in magnitude also. So kind of the stability of this problem is, it loses its stability for eta larger than eta max when this thing is positive.
Yasaman, there is a question in the chat, but I'll read it to you because I know it's hard to read when you're full screen. It says, how does the mechanism translate to the more general case? I guess the question is sort of not necessarily about the experiments, but whether you can analyze the more general case in similar ways.
Yeah, I have like we have it in our paper. I have like one slide on it, which is again kind of approximate. It has like the key parts in there, but it's not like a precision analysis because we kind of get out of this model what we want. Before I jump to that slide, maybe I'll just point out a final thing, which is that the kind of purpose of this was that you kind of needed to solve the dynamics first before making the networks wider to get this particular fixed point of the dynamics rather than the other way around. So there's something kind of not commutative, not exchangeable between these two limits. If we take for any finite time n going to infinity first, for any finite time that doesn't depend on n, if we take n going to infinity first, we're going to collapse back onto the NTK solution. But if we allow our time scales to kind of grow with n, then we kind of jump over to this other fixed point of the dynamics, which is very different from NTK, where we end up with kind of much lower final curvatures. So to answer that question, I'll skip this slide because it just shows that in this very simple model that I just went through, you reproduce the phenomenology that I talked about earlier. So in the full model case, what I want to show is basically we have these updated equations for U and V. This is the form of theta and some other variables I've defined here, F tilde and zeta. But what you see in the function space updates is that they're very much not closed, so they're harder to treat, of course, theoretically. You can make some partial approximate progress basically by kind of looking at this evolution projected onto the top eigenvector of the NTK. So the idea is if you're starting out at init, the second term is kind of order, again, 1 over n, just like I showed you in the fully scalar case. And what this term is doing is kind of projecting you onto much more rapidly onto the top eigendirection of the NTK. So if you kind of make the approximation, if you decide that you're only going to study kind of the projection of this is an error vector now. It's kind of the difference between F and the labels. If you project that onto the top direction, you can get some scalar equations that are very reminiscent of the ones that I showed you. And similarly here, kind of project it into, take the inner product on both sides with F tilde and then project that onto the top eigenvector direction. So here's kind of a partway equation to Flash where you've contracted theta with F tildes on both sides and it's starting to look like the scalar equations. And then if you further make the assumption that F tilde is sort of like the maximum eigenvector or is close to that, then you kind of reduce it to the scalar equation, which, you know, if this were like an F squared here, then we would recover the equations I just showed you. And this theta term does behave like F. The definition of its definition is here. So it's something that kind of, when F grows in norm, or F tilde grows in norm, then theta does as well. And so this kind of roughly has the same behavior as the scalar equations I showed, although again, not like, it's not a precision kind of comparison. But the mechanism here is sort of that if you kind of focus on the projection of the error vector onto the top NTK directions, that you can kind of recover some part of that original analysis. So I hope that answers that question about the mechanism.
So what about, so what complicates the picture if you have nonlinearities?
So in this particular setting, I think here in the definition of theta, it might be harder to deal with. I believe, although I haven't thought about this in a while, that if you had nonlinearities here, it might be harder to kind of contract with F tilde and recover something similar to the scalar case.
Okay, I see.
In the yeah, I'll say that is my memory of it, but I would have to, don't quote me on that.
Sure.
Yeah. And finally, I guess how does this connect to generalization? So coming back to this point about being motivated by performance that I mentioned early in the talk. So these two different phases greatly affect the final curvature. We found that these differences at early times often have implications for late time dynamics, even for finite width models, where you don't necessarily have control on the late time dynamics unless the model is pretty wide. For plots that I want to show between performance of lazy and catapult phases, I want to make a side remark, which is that I guess, oftentimes when people compare, or what we had seen in previous literature that compares small and large learning rates, oftentimes it's done for a fixed step budget. And so this plot on the right here is for a fixed step budget. And you see that in the green regime, which is the catapult phase, you get better performance. But I think you could ask two different questions. One is like, do larger learning rates perform better just because they train faster? And like, if you gave a smaller learning rate model enough time to catch up, would it do as well as the larger learning rate model? So we did ask that question. So a lot of our experiments are done for two different kinds of comparisons, both like a fixed step budget and also a same, physical time budget, which means that we measure time scaled by the learning rate rather than just the step. So time here is eta times the step. And so that allows smaller learning rate models to train for longer. I guess how you decide to define time maybe, or kind of allow these smaller learning rates to catch up, maybe sort of depends on what kind of dynamics you think is most relevant, like whether you think you have drift dynamics or diffusive dynamics. But so like the scaling kind of linearly with eta and step is something that we chose and compared models, did both kinds of comparisons. And in those settings, we still saw that in certain cases, like larger learning rates did do better, even when they're evolved for the same amount of physical time. So here, just a sample of some of these kind of results. The one in the middle and on the right are wide resonant models, CFAR 10 and CFAR 100, in kind of more sophisticated settings. And both of those are models that are evolved for the same amount of physical time and also have some learning rate decay at the very end. And you see again that once you allow for decay and some convergence, that in general, the performance is a little bit better in the catapult phase. And it really depends, I think, on the regime you're working in. So this plot on the left, when you have just a small number of samples, 512 MNIST samples, does a lot better in the catapult phase than the lazy phase. But so like whether you see this large performance gap between the two regimes is really a strong function of how wide you are, how many training samples you have, and maybe other architectural aspects. Yeah, but in general, we think that the larger learning rates, because they lead to lower curvatures at the end of training, typically have better performance, and or if you like, because the NTK is allowed to evolve and you're allowed to do feature learning, although we haven't really defined what that is here, whether that is the same thing that we're actually talking about in the catapult phase is kind of unclear. I just talked about like a change in sort of the scale of the problem. Feature learning might be something different. I don't know. I think that's an interesting question. I think I'm running pretty over time. I want to say maybe just I have like 2 more slides. Is there time for 2 more slides?
Of course.
Oh, okay, great. So yeah, just the fact that we also believe that this transition corresponds to a breakdown in perturbation theory if you're in the infinite width limit. So like the transition between these things is sharp in these limits, but at any finite width, it's a crossover. And so the way it typically is in physics. And so, testing it is maybe, yeah, I guess there are some subtleties. There would be some subtleties there if you wanted to test it, but roughly we think kind of if you looked at any of these kind of earlier expansions, perturbation theory that was done for how neural networks evolve under gradient descent, kind of using the Feynman diagrams or the neural tangent hierarchy, kind of similar ideas. What you would find is that kind of there are terms in that expansion that would all be roughly of the same order. Because f grows to be of order root n, and that kind of breaks, that basically kind of kills the expansion. Yeah, so that's something that could be made more precise. We think it's true. I will say that I guess if the model is wide enough, that would also mean that after this period of time that we refer to as the rearrangement, when this catapult happens and then the loss goes back down and the curvature kind of starts to stabilize, if you linearize a model or do a series expansion of the model after that point, then your perturbation theory would be valid. This is maybe like one empirical test of it, which this plot is showing. If you take the blue, the dashed blue, and the red show an overlap between a nonlinear model and a model that is linearized after the catapult phase, so that there's agreement between the two in this setting. But if you linearize kind of at step 0 at this learning rate, the problem just diverges anyway. And so if you linearize after the catapult, you know, you maybe can recover the dynamics of the original model. Although, again, fleshing that out what that actually means is a bit more subtle, and I won't go into that.
I'm sorry, do you have experiments for more complicated networks like wide resonant or something?
Not in the paper.
So so I guess like I'm wondering, here you say you're linearizing a step 10, and I guess same test accuracy as the linearized 0. Oh, sorry, the non-linear version. But I suspect that this won't be true for a wide resonant.
Yeah, I think that's true. I don't know that I don't recall if we did wide resonant or not, but
anything you have batch norm in, I'm almost certain that step 10 you will not get this.
Yeah. Also, so I have no claims about batch norm, but thank you for pointing that out. I trust even for a setting where you didn't have batch norm, I'm not sure I would want to see more experiments to really believe it.
Yeah.
This is like a simple setting where a small number of samples and there's good agreement. Yeah, but thank you for that question. Yeah, I agree with you.
Okay, sounds good.
Yeah, particularly, so the thing is, I did the wide resonant results I did show for the catapult do include batch norm, even though we don't have, I don't have any understanding really of what happens with batch norm.
The claims are different, right? Here you're claiming that if you linearize a step 10, then you get all the feature learning, whatever it is, that you get without linearizing. But there you're really saying like, oh, here with large learning rate, you get good performance. Like they're not, the experiments justify different claims.
Well, but even the behavior of the like the fact that you see a catapult kind of in one of the wide resonant plots where I showed like the loss kind of going up, the fact that that happens even though all of, I don't have a theoretical understanding of kind of the infinite width limit of that model. So why necessarily should the loss go up and be controlled? Kind of why should the transition be close to 12 over lambda naught as it is for like all the non-batch norm models? So like that sort of thing, I think we only understand it really in the non-batch norm setting using and expand, these equations that are motivated by large width, even if batch norm, I don't know how it actually behaves.
Right, so like, but that's the claim on the dynamical stability of the process. But here, claiming something different, right? That if you linearize a step 10, you get the same performance.
But what I guess I don't, because I don't, that's true. They're different claims somewhat. And this one is not fully, this one is related more to the perturbation theory. But even that other claim, I only understand the stability of that problem with equations that involve no batch norm and are related to like NTK dynamics at an infinite width. And I don't know what happens with batch norm. So like, therefore, I don't know if I can trust those equations to tell me about the stability of a batch norm network.
I see.
Maybe,
sure.
but
I get you, yeah.
But I would be curious to hear kind of more of your thoughts afterwards.
Sure.
So yeah, this is kind of our thoughts about the perturbation theory. And then finally, the sense in which it's a phase transition. So I mentioned kind of this, the final curvature as a function of the learning rate is constant when you're less than kind of 2 over lambda naught, but it decreases when you're at larger learning rates. So this is some kind of non-analytic dependence on the learning rate if you're allowed to be in this double scaling limit of width and time. So that you can kind of probe for learning rates that are larger than eta critical. And if you look at some quantity like number of steps till convergence, for instance, so this is T star as a function of eta, you'll find that on both, at least in the simple model, on both sides of the transition, you'll get like kind of a critical exponent for that dependence, which is 1. And you see this kind of here in the plots. although some of the numbers are kind of so-so on both sides, you get the kind of -1 critical exponent on both sides of the transition. And you see that here kind of in the numerics, which are done on the toy model. Okay, and so I'll close here just to kind of recap of what we got out of both the empirics and the theoretical analysis. We think these signatures are pretty universal, at least like the growth and the loss, the drop in the curvature, the fact that it happens on a time scale which grows logarithmically with width, which we've also tested. I didn't show, but we've kind of tested in scaling experiments. It's surprising that kind of the number C is kind of small or largely the same for a large class of networks, and it's exactly 4 in this simple model. We think this sort of thing is helpful potentially for hyperparameter tuning, whether you want to be in a lazy phase or a catapult phase, and what kind of final model you would like to have. But this simple model really highlighted maybe the need for like a double limit, and also maybe is inspirational towards ways of kind of saying some more detailed things about the evolution of the kernel in this catapult phase for more general settings. I think would be interesting. So I'll end there.
Great, thanks, Yasaman. So people who are still here, yeah, questions, please. So I see Julian, you have raised your hand, so feel free to speak.
Yeah, can you hear me?
Yes.
Okay, yeah, first of all, thanks a lot for this very interesting talk. This whole infinite width limit is kind of new to me, but I have a question which somehow comes from the direction of renormalization group theory. So if I understand you correctly, in the lazy phase, if you go to the infinite width limit or continuum limit, it would be a trivial fixed point, so a Gaussian fixed point. And in the divergent case, you would just have runaway trajectories, and in the catapult phase, you would have some kind of non-trivial, manifestly non-Gaussian fixed point in this limit. Would you agree with this intuition?
Is the fixed point that you're describing fixed point with dynamics with respect to both like take infinite width limit or take one of these limits and also solve the dynamics? You're not just talking about the initialization, which is where...
No, I also mean the dynamics, yes.
Yeah. So I think that's roughly true, but in the NTK phase, it evolves to some other Gaussian field, if you like, with time, which you could also write down in closed form. The fact that happens is, of course, because the fact that you even have it analytically is because you use MSE loss. So the field would evolve differently if you were using, say, like cross entropy loss or something like that. And then could you say again what you said about the catapult phase?
Well, I just assume that the catapult phase, if it has a fixed point, it must be a non-Gaussian one, which probably cannot be described perturbatively as well. But it's a situation similar to what we have in QCD, for example, in physics.
Yeah, it is. I do think that it's non-perturbative with respect to the initial kind of Gaussian field, but I don't know how to describe it actually.
Okay.
Yeah.
I'm asking because the way this is approached, at least in lattice quantum field theory, is that if you want to take the continuum limit, but you have finite resources, so you can simulate infinitely many points, you drive your system towards a second order phase transition where you have self-similarity, so you can observe some continuum scaling. So you get the continuum physics. I'm wondering if the same can be done here. So with a finite network, you set the hyperparameter such that you drive it towards a phase transition where you have criticality. And then using the self-similar scaling, you can observe the infinite width scaling if you wish. But that's pure speculation, of course.
Okay, I would have to think about how to actually do that. Yeah, it's not, I mean, that's a interesting suggestion. I honestly hadn't thought about kind of that sort of angle on the problem.
Okay, thanks a lot.
Yeah.
So there were some other people who raised their hands. Just, I guess, I can't see who raised. Oh, actually, I do. Jeremy, I guess. Jeremy.
Hey, can you hear me?
Yes.
Hey, Yasaman. I'm wondering, is that like so the lambda naught parameter? Is that like an intuitive way to describe how that depends on any other properties of the network, like the scales of the weights, or is that like an intuitive way of understanding how that depends on other stuff?
Yeah, there is, like, well, in the I don't have intuition for the general case of NTK. In the simple model, that scale lambda is just u squared plus v squared times over 1 over n. So it's the norm of related to the norm of the weights, and so kind of if lambda drops, then the norms of the weights drop.
And is it the squared? Would it be square root of u squared plus v squared, or was it u squared?
It was u squared plus v squared over n equals lambda.
I see.
But in the, I think tracking kind of the kernel or things that are related to the kernel is more natural than tracking things that are related to the parameters. So like finding the right quantity kind of in the kernel space, you know, maybe like the top subspace in this more general setting, the higher subspace of the kernel, you know, how, if it's like degenerate, maybe kind of the top K subspace of the kernel, is like the more natural, I think it's more natural to find quantities basically which are related to the kernel and then back out what's happening to the parameters rather than the other way around, just because I think this is sort of like, this is easier to analyze somehow in the function space picture, I think, for me at least.
Thanks.
Okay, Jamie. Jamie,
hey.
You have a question?
Yeah. So thanks so much for the talk. I had a question actually about your intro material. So you mentioned that you can view the output of a large, like in the infinite width limit, the output of the neural network is like a Gaussian process as a function of the input data x, and then with the weights random and fixed. But I'm wondering if you instead take the input data to be random and fixed, can you view the output as a function of the weights as a different Gaussian process with a different kernel? I mean, it would be non-isotropic, but.
Random and fixed, and then what's happening to the weights? The weights are fixed?
No, so instead of looking at the output as a function of the data, you look at the output as a function of the weights. So like, sort of like the loss landscape, but not the loss, just the output. Is that also a Gaussian process?
It's an interesting question. Off the top of my head, I would want like another minute to think about it.
Okay.
So I don't think I'm going to give an accurate answer.
Like, what is your assumption though? So in the Gaussian process result, the assumption is that you're randomizing your weights. Your inputs, you know, input comes from this input space, but you randomize your own weights, and that causes the function to be Gaussian distributed. But in your formulation, I mean, the weights they cannot be random because they're the input.
Yeah, no, exactly. So you
distribution on the data.
Yeah, so it would be something like maybe instead of the weights being random and Gaussian, the data was random Gaussian white noise or something. And the reason, my motivation for asking is that people, in looking at, in arguing that there are things like no bad local minima, people draw comparisons between loss surfaces and Gaussian processes, but that the Gaussian process is over the weight space, not over the input space. And I just never, I'd only seen the argument that you gave, Yasaman, where the Gaussian process is over the input.
Yeah. Yeah, no, that's a good, I think I know which paper you're also thinking of. Yeah,
maybe you have different thoughts, but at least it seems to me like generically, you cannot expect it to be a Gaussian process in the weights. I mean, just because, I don't know, like say a linear network, right? And you have the input, and then the dependence of the output on the input is purely through like this data that is multiplied only at the beginning. And there's not enough randomness to at least achieve the central limit behavior.
So I think there, in just a simple linear model case, I'm understanding what you mean. Then if you had one random data sample and one scalar output, then the output surface would be just like a random linear function of the weights, and that is a Gaussian process. It's just, I mean, we have sort of a weird kernel. But I don't know. This is maybe
you're right. In the linear case, that's true. In the nonlinear case, I will be surprised if that's the case. I mean, in the linear case, it's kind of trivially the case, but
yeah, no, I don't expect it to be true in like a finite size case, but I don't know, maybe in some limit. But this question's sort of diverging. I think other people maybe should have a chance to ask things. Thanks, Yasaman.
No, but it's a great question. Thank you. I think I need more, like another minute to think about it.
Yeah, would you mind if I like emailed you just so
Sure.
in case you think of something? Then
Yeah.
Cool. Thanks so much.
cool. Any more questions? Feel free to just shout it out now. Okay, cool. So then thank again to Yasaman for the wonderful talk. And let's reconvene 2 weeks from now. All right, thanks everyone. Have a good Wednesday.
Thank you.
Thanks for the talk. And thanks, Yasaman.